Welcome to day 7 of our Principles of Programming Languages course. Today we will be diving into data types and type systems. Let's explore how different programming languages handle data and types and the importance of understanding these concepts. In this session, we start by understanding what data types are and their significance. Data types determine the kind of data a variable can hold and are fundamental to how programs handle and store information. They play a crucial role in preventing errors and improving program efficiency. Data types can be categorized into primitive types and derived types. Primitive data types are the most basic types such as integers, floating point numbers, characters, and booleans. These types serve as the building block for all programming languages. Derived data types include arrays, lists, pointers, and strings. These types are built using primitive types and allow for more complex data structures. Abstract data types, ADTs like stacks, queues, maps, and sets offer even higher levels of abstraction. How is data represented at the machine level? At its core, data is stored in memory, and understanding the memory alignment and size considerations helps programmers optimize performance and avoid errors. Different languages may represent different in various ways, but the underlying principles are the same. Now let's talk about the type systems. A type system is a framework that defines how variables and expressions are assigned types and how these types affect program execution. It governs everything from memory allocation to error handling and performance. In programming, you often encounter strong and weak typing. Strong typing means that a variable is strictly enforced to hold a particular data type. For instance, in Java and Haskell, you cannot assign a string to an integer variable. This helps catch errors early in the development process. On the other hand, weak typing allows implicit type conversion. For example, in languages like JavaScript and PHP, you can assign a string to an integer variable, and the language will automatically convert it to the correct type. While this flexibility can be convenient, it may also lead to unexpected behavior and bugs. Now let's compare static and dynamic typing. Static typing, found in languages like C and Java, checks the type of variables at compile time. This means type errors are caught before the program runs, which can result in faster execution and fewer runtimes. Dynamic typing, as seen in languages like Python and Ruby, allows variables to change types at runtime. This adds flexibility and can make development faster, but it also introduces the possibility of runtime errors if types aren't handled properly. Type checking can happen either at compile time or runtime. Compile time checking ensures that type errors are caught early. On the other hand, runtime checking occurs when the program is executing. Both approaches have their pros and cons, depending on the language and use case. Type interface is a feature in many modern programming languages where the compiler automatically deduces the type of a variable based on the value it's assigned. This can help reduce boilerplate code and make code more concise while still maintaining type safety. Nullable or optional types are a feature in languages like Kotlin and Swift, which allow a variable to be set to null or none explicitly. This reduces the risk of null pointer errors, which can crash applications if not handled properly. Enumerated types allow us to define a variable that can hold a specific set of values. For example, the days of the week or the states of a process. Enums provide better readability and prevent invalid values from being assigned. Pattern matching is a feature often used with enums, especially in languages like Rust and Haskell. It makes handling different variants of data easier and more expressive, leading to cleaner and more maintainable code. Polymorphic types such as generics allow a single function or data type to work with multiple types. This ensures type safety without sacrificing flexibility. Languages like Java and C# use generics extensively to allow developers to write reusable and type-safe code. Let's look at some real-life examples. First, basic calculations with primitive types. For instance, you can perform arithmetic operations with integers or floating point numbers. These operations are essential in most programs. Data storage examples include using arrays or lists. For example, creating a list of student grades or managing shopping cart items. These data structures are fundamental in nearly all applications. In this section, we have some hands-on exercises. We will explore static versus dynamic typing, type interface in practice, and implement a generic container in languages like Java or C++. These exercises will help reinforce the concepts we have covered. To summarize, data types and type systems are essential for ensuring that your code is correct, efficient, and safe. We discussed the differences between strong and weak typing, static and dynamic typing, and how type checking, in inference, and nullable types contribute to robust programming. That concludes today's session. Now I would like to open the floor for questions and discussion. Feel free to share your thoughts on how different type systems impact your experience with programming.